Okay, in this next area, we're going to be talking about entropy. Okay, and what is entropy? Okay, I like to use one word that's very easy to understand: randomness. So entropy is randomness. Now, you might think that since heat is produced in exothermic reactions, that they're the only spontaneous ones, but that's not always the case. For instance, when you dissolve baking soda in water, if you remember the bad chemical reaction experiment, it got cold and it's spontaneous. Okay, so what is allowing that to happen? Okay, let's think of, again, our example about ice melting. So if we have ice melting at 25 degrees, a little bit warmer than room temperature, it's endothermic. It absorbs 6 kilojoules of heat. That's why the table it's on or your hand is going to get cold as the ice melts. So the enthalpy change is endothermic. So it shouldn't do it spontaneously if it was only if it releases energy. So what else is happening? Well, some other factor must be influencing the spontaneity of this. And it's related to order. Remember I said randomness? So entropy is a measure of the disorder of a system. The law of disorder states that the natural tendency is for the system to move in a direction of increasing disorder or randomness. So for some of you, maybe this looks like your bedroom floor. Okay, maybe you just throw your clothes on the floor until mom comes and picks them up or makes you go and pick them up. Okay, so randomness is the natural happening of everything. Okay, so here's an example of a dog walker. All the dogs are orderly on their leash. She lets them go and they run all over the dog park. Now they're free to run. So they've increased their randomness because they're all over the place. So when the entropy increases, as reactants form products, they tend to be favored. So in other words, if entropy increases in the products, then that's going to be the favored reaction. So if we look at ice again, here's a nice ordered solid, there's liquid, and then there's gas. Remember my KMT dance, all right? So my solid is very ordered, very low entropy. Entropy increases in the liquid state and increases more in the gaseous state. Okay, we can also increase entropy by breaking apart our solid. So increasing surface area, okay, can also do that. Or when we dissolve it in water, we're getting all this apart and everything is dissociating. It also increases if we have two particles, for instance here, and we end up with 3 particles here. So if we increase the number of molecules in our product side, or whatever side has more, that's going to be the side with more entropy. All right, so if we look at this, we have 2, and here we have 1, 2, 3. So that's going to increase the entropy. The next thing we're going to talk about is when we increase the temperature, because if we increase the temperature, the molecules are moving faster. If they're moving faster, they're going to be all through the container because they're going to get more kinetic energy, which means that they become random more random, and the disorder increases. Entropy increases. Okay, so now I want to have you look at a series of 4 equations. Pick out the one where entropy increases based on the concepts we just went over. I'll catch you on the other side. Did you answer A? We have a solid, 1 molecule, or 2 molecules, and we basically have, let's go back, we have a solid, okay, doesn't want to get this pen going. Okay, so we have 2 molecules of solid, 2 molecules of gas, 4 of a liquid, 1 of a gas. So we're going from solid to gas more than what we started with. Everything is more entropy. So everything is changing. The number of types of particles, the number of molecules. We're going from solid to liquid and gas. The other ones, we go from gas to liquid and less particles, gas to gas, gas to liquid. We're getting less again, and so on and so forth. Okay, so if we look at this one, we have 6 particles going to 7, so that should be an increase, but we only have 3 that are gas. We have 5 that are gas there. 6 to gas, so it's a decrease in entropy. This one we have 2 solids and 1 gas and 1 liquid, and we're going to solids and less of them, so that's more complex, so it's getting away from more entropy. Okay, enthalpy and entropy are the 2 factors that will determine if something is spontaneous. So we have to consider both. The size and the direction of the enthalpy changes and entropy changes determine whether a reaction is spontaneous. So we need to know what's happening in both cases. Usually it's the enthalpy that's the most important because it has oftentimes a larger amount of energy is in the enthalpy term. However, it's not always the case. Okay, so if we have an exothermic reaction in which entropy increases. So in this case, exothermic is a plus, is basically towards being spontaneous. And the fact that entropy increases, that also means it's spontaneous. So both factors are favorable, so it's going to be spontaneous. Okay, if we have a decrease in entropy, is offset by a large release of heat. So that little bit of decrease, we have a big exothermic reaction, so it's still going to be spontaneous. And if we have an increase in enthalpy by an increase in entropy, it's also going to be spontaneous. Now when I say an increase, if we look at the delta H, that's still going to be negative. So if we're saying increase in enthalpy, that means energy release. Okay, more energy release, just so you know, because sometimes that increase-decrease is confusing with the signs for enthalpy. So here's a little chart to tell us when the reaction will be spontaneous. So if the enthalpy change decreases, okay, well, let's go back to the original slide here. Okay, yeah, we said the same thing. All right, so if enthalpy change decreases, it becomes more negative, it's exothermic, and entropy change increases, more disorder, that's always going to be spontaneous. If we have an increase or an endothermic enthalpy change, okay, and an increase in entropy, it may be spontaneous only if the enthalpy change, which is not favorable, endothermic is not favorable for spontaneity, by a favorable entropy change. So the entropy must make it so. Now if we have a decrease or exothermic and the entropy also decreases, which means there's more order, then only if the entropy change is offset by a favorable or higher enthalpy change. And finally, if we have an endothermic reaction and a decrease in entropy, it will never be spontaneous. Okay? So let's look at this reaction. This is going to be on educannon. So we have potassium chlorate going to potassium chloride and oxygen. Is this going to be favored based on what we've discussed? Okay. So I hope you answered that 2 molecules of KClO3 solid are making 2 molecules of KCl solid, but also 3 molecules of oxygen gas, which is more entropy. Okay, and we said it was exothermic, so both things are favored, so it will be spontaneous. The next thing we're going to talk about is something called delta G, or free energy, the change in free energy. Okay, free energy is G, and the delta means change, so it's free energy change. And we can use this value to tell us if a reaction is spontaneous. Okay, this is often called the Gibbs free energy. Okay, and it was named after someone called Josiah Gibbs. And as I said, Gibbs free energy is G, and it can either be released or absorbed during a physical or chemical process. So we come up with an equation, which is right here. So we have delta G, which is the change in the Gibbs free energy, and we have that's equal to the change in enthalpy minus the temperature in Kelvin times the change in entropy. Okay? So I call this the ghost equation. That's how I remember it, because it starts out with G, then it has a delta H in it. The 0 kind of is my minus sign, and then I kind of change the T and the S around so I know to put a delta S, because the H, the G, and the S always have a delta in front of it. But the ghost is a little, kind of like a nice device that I use to show me what the reaction is. Now, this is the important part to remember. If delta G is negative, the process is spontaneous. If it's positive, it's non-spontaneous. So, if we have this question, which I'm going to have you answer on educannon, the entropy change for the following reaction at 298 K is 3.0 joules moles per Kelvin, moles Kelvin. And the enthalpy change is minus 394 kilojoules per mole. This is the equation. Calculate the Gibbs free energy change and determine whether the reaction will occur spontaneously. Okay, the only thing I want you to be really careful about when you do the ghost equation is this is kilojoules and this is joules. So when you use them in the equation, you have to decide, are you going to use joules or kilojoules? You have to convert one of these to the proper term. All right? Okay, go ahead, try it out, see what you get. Okay, so I hope this is how you went through it. You had minus 394 kilojoules per mole, minus 298 Kelvin times 0.0030, because that we have to divide by 1,000 to get this into kilojoules. When we do the math, we see that the delta G is negative, and the reaction would be spontaneous. Okay? And let's look at some of the key concepts to finish up. You might want to take a screenshot of this. There's the ghost equation. Here's some definitions. And remember that enthalpy and entropy are used, as I mentioned in the opening of the videos, that can be used to determine if a reaction will occur naturally or not. And that's it for Chapter 18. See you in class.